Assalamualaikum and good day all. Today I would like to introduce chapter 7, discussing about the magnetic force and field. Actually, this one part of the chapter 7. The first part we will discuss about the magnetic force and the field. So the second part we will discuss about the electromagnetic force and field. But this first we discuss related magnetic with the electrical. Okay. Okay. In the magnetic poles, we have the every magnet have two poles, north and south, and it's therefore called dipole. Unlike electric field, it's impossible to have a monopole. If you cut of magnet in a half and up, you will get the dipole also. So the first we can see in the red mentioned on the north pole, and the second one in the gray color is the south pole. So it's mean if you cut by half, for example, I will take the north part and then I will cut separate by two pole also, north and south. So we cannot separate. So every magnet will create the pole. Okay. We turn, rotate, and should be like this. Also will create two pole or dipole. Okay. Okay. Actually, in the our Earth condition also construct by the magnetic field in the within the north and the south. So if you see, we refer the north pole, we can see the compass will mention the direction of north to the south. So compass will mention the north to the south of the north of pole. Okay, because north and south will attract each other. Okay. Magnetic field lines, magnetic field. So actually, even we cannot see by naked eyes, the magnetic field will create the field like this within the north and the south. This region space where the test magnetic experience in a turning force. Okay, actually we can try this line by the magnetic powder. We separate within the magnetic. So the magnetic powder is actually the iron or ferro particle. We can distribute around the particle of magnetic ferro will create the pattern like the electric and magnetic field. Yeah, so it should be like this. Okay, magnetic flux density, or we call in notation in B, the strength of the magnetic field seems like to the density of the magnetic field line. There is a stronger field at the poles where there are more field lines. So we can describe the magnetic field flux, the density is around north, south, and also north. So the magnetic will carry the flux. So the density is mean the power of magnetic itself. So the magnetic flux density is the equivalent to G for gravitational field. Gravitational field is mean in the unit Newton per kilogram. And then electric field in the E is Newton per coulomb. Yeah, coulomb. So the unit of magnetic flux, B, is in the Tesla unit, and like the other, field strength is a vector. So we will mention the direction. This means have the vector condition. Vector will be have the not only the quantity, also the direction. A good way to think about is that it is just a measure how many field lines there are in certain area. A magnetic field is often called a B field. Okay. Until we know more about magnetism, it isn't be possible to define the magnetic field density in the same way as we do gravitational field strength and electric field strength. Okay, we have right-hand law to actually to describe the direction or condition in the magnetic with the current relationship between the current and the magnetic field. So actually, the current and magnetic have the correlation. So field caused by current actually. So by the field of the magnetic will carry out the current condition. Yeah. It turns out the small compass is placed near the wire carrying a current. It experiences a weak turning force. Certainly, the attraction of the compass will carry out the magnetic field by magnetic field itself. So if we use the compass nearest to the current work, the compass will be affected the direction or will be disturbed the direction of compass itself. So it means the current and the magnetic will have correlation. This led scientists to realize that magnetism is actually caused by moving charge. So the field is strongest close to the wire. The direction of field can be found using the right hand corkscrew rule. So we can use by right hand here. So in the thumb direction, mention the current direction. So while the other finger describe the field direction condition. So actually the field is perpendicular to the current direction. Field inside the coil. So if where we use the coil, while the coil will through the current inside of the circle. So what happened? When the current flow around the circular loop, the magnetic field form a circle. All these circles add together. This make a really strong field in the center of the circular loop. So it means if we flow the current inside of the circle, so the magnetic will carry it in the magnetic field will carry it the inside of the coil. So what we make the much of the coil, so we call solenoid. So a solenoid is coil of wire carrying the current. So we will flow the current inside the solenoid. So what happened? So we'll carry out the electric field. So if we starting the current from the left side here in the second figure to the right side, so the source should be in the left side. So the north will be in the right side. So because the flow of the current will be create the pole. Okay. So the direction starting consider a source, and then the end of the current is considered as north of pole. So we have an experiment here to measure or to carry the direction of the magnetic with the direction of the current. Okay, example one. We have a battery here with the magnetic condition. So we will go flow to magnetic field from the positive here. So what happened? The node will be carried in the left side. So because of the flow of current. What about we try to reverse? We try to flow from the positive, from the right side to the left side. So what happened? Change the node or the pole. So we the node will be changed from the left side to the right side. So because of the flow of the current. Okay, we can use the Fleming left-hand rule to describe the magnetic field with the current condition. So this left side is to describe a relationship within the current and the magnetic field. So it's possible to predict the direction of force acting on the wire, its motion, if the direction of current or the magnetic field are known. Fleming left-hand rule is used to do this. So we have thumb here, and we have the direction finger here, and then a middle finger. So the thumb is described the force, about the force of the current with because of the first finger mention the magnetic field, and then the second or middle finger will mention the current. So we will create the force. So the force will be push or attract from the other current condition. Okay, we can let's see later how to the force acting, and then we can calculate the force in the from the figure here. We can calculate later on by using the formula. Okay, how to the force acting? How can the size of the force be increased? Increasing the size of the force. So the size of the force acting on the wire depend on the three factor. Okay. Okay, the force is influenced by magnetic flux density, current in the wire, and the length of the wire. So we just use the left hand to describe this condition. So the force is actually perpendicular to the field or the field of current and also magnetic field. So force will be carried the power by influence of the magnetic flux itself, and then the current itself, and then the length of wire. So you can see, so if all parameter, this parameter higher, so will be increased the force power. So it means F is proportional to all three parameters, these parameters. Okay, how to the simplify of the force formula, we can see if the current, we can rewrite as the Q charge over the time. So we can simplify to change, replace the I current by Q per T. And then we can simplify again, L per T. So L is the distance, T time. So distance over the time, we can change the velocity. So we can change L over 2T is by the velocity of the electric charge. Okay, now we can see the charged magnetic field electron moving in the wire. Actually, if we consider positive in the in the left side, and then negative to the on the right side, actually the electron will be moving from the left to the right. Actually, even the current will go from the left to the right, and the electron will go from the opposite way. Okay, we can see from the arrow here. So electron moving freely through the magnetic field. So actually, every magnetic field will moving by electron to electron. What force are there between two current carrying wires? Step 1, what does L1 to the L2? So use the right hand. We can corkscrew rule to see what the field lines do. You can see, okay, a current here in the wiring direction flow from the left to the right side. And then we use the left hand rule, we can describe. So the force is perpendicular to the current, and then we'll also carried by electric field here. So also perpendicular to the current here. So we can describe. So the force will be acting to other wire. So careful if you play with this one. So the force will be acting. Okay, now repeat for the other wire, L1, the L2. So we change the condition. The first one, we use the lower one, and then the second one, we use the electric field on the upper one. So the force will be acting from the wire. We create the magnetic here, so the force will be acting to each other. So we'll play with the positive and negative. Okay, this one, same like battery. We have the battery from the positive. Actually, we describe the positive in the red one, and the black is considered as the negative. Okay, this one is solenoid, and then we give the flow through inside the solenoid. So we'll carry out the magnetic field also. So we can create we can describe the condition actually, what happened, even we cannot see by the eyes. So you can describe this one by simulation. Okay, in the end of this presentation, so I would like to discuss about some of examples here. So the relation between the solenoid, current, and electromagnetic field. So we have example here, the example one. A step-up transformation has 5 loops on its primary coil and 20 loops on its secondary coil. If the primary coil is supplied with an alternating current at 120 volt, what is the voltage in the secondary coil? So actually, the condition described have 2 conditions of solenoid, same like just now in the previous of theory. We have 2 of solenoid to create the force, right? So the first we call a primary coil, and the second is secondary. So the first primary is have 5 loops, right? And then in the secondary we have 20 loops. So how to correlation within this formula condition by formula Vs over to Vp. V is as we know as the alternating current or the voltage potential. Vs over to Vp equal to Ns to Np. N refer to number of solenoid. So we can simplify the formula from this formula to the unknown or the question. So the question, voltage in secondary coil. So we just carry out the Vs. So the Vs formula can be as Ns times to Np divided by Vp. So we can calculate this example, and then we can get the number of voltage for secondary. Okay. And then the second of example, still in the force formula, a conductor of linear mass density is 0.2 gram per meter suspended by 2 flexible wire as shown in the figure. So suppose the tension in the supporting wire is 0 when it's kept inside the magnetic field of 1 Tet. This one is a Tesla, whose direction is into the page. Compute the current inside the conductor and also the direction of the current. Assume gravity equal to 10 meter per square second. So this one is condition the electric field. So this one consider the higher, the length consider positive. This one is considered to negative. Okay, how to solve? By given data, linear density, meter over to M is mass over to length. So equal 0.2 gram per meter. So we can convert from gram into the kilogram. So by 0.2 times 2, 10 negative 3. And then power, 1 Tesla. And then gravity, 10 meter per square second. So based on the formula of the force equal to field, magnetic field, and then current, and also the length of wire. So as we know, another force in the Newton law equal to M to G. So we can compare. So F equal to F, F of the force of in the electric field, and then also force in the Newton law. So we can get the current from this formula. Okay, now we can get the current equal to 2 meter ampere. Sorry, 2 meter ampere, correct. Okay, this one is the last example how to implement the formula of force. Okay, we go to direct of the example. A circular coil with cross-sectional area 0.1 centimeter square is kept in the uniform magnetic field of strength 0.2 Tesla. If the current passing in the coil is 3 ampere and plane of the loop is perpendicular to the direction of magnetic field, calculate A, total torque and the coil, and then total force on the coil, average force on each electron in the coil due to the magnetic field of the free electron density of the material of the wire is 1028 meter in the per meters cube. Okay, by given data, we can simplify parameter like this. And then we go to the question, torque of the coil. So theta sin perpendicular of the coil. So this one is actually, we will discuss later on this formula, the torque. Yeah? So the formula torque is, later on we can discuss in the second part of the chapter 7. Okay, B times to current times to L sine theta. Okay, and then we can go to the total force of the coil. Actually, the second part of B I would like to discuss. So F equal to B I L sine theta. So net force of plane loop in the magnetic field always zero, as net force the couple of zero. So if yes, sine theta is perpendicular, so we consider as zero, sine theta. Okay. So now we go how to implement F equal to BQV. As we know, we can simplify the F equal to BQV because we can replace the current by Q over to T, and then Q over to L equal to the velocity. So we can simplify the formula like this. So we have two questions here, two formula here. The first one FBQV, and the second one EVD B sine 90. So we can compare this formula, and then we can carry out the VD. So like this. And then the F equal to BINA. N is number of electron, and then times to area. So we can answer the force is 0.6 times 2, 10 power negative 23 Newton. Okay, that's all for first part of chapter 7. So I see you in the next part of chapter 7. So I hope you can simplify or summary from this presentation. Thank you. That's all.